And if you're a condensed matter physicist or field theorist on a discrete lattice, the way you think of it, space has been replaced, continuum has been replaced by discrete points marked by, label 1, 2, 3, 4, 5. On each one of them, there is a field. Here it's between 0 and 1. And a kind of thing which we do when we take a finite block, we have some configuration of the fields, and then we say, well, we actually care about infinite spacetime, but we are tiling it by repeats of this block. That's also when you teach quantum mechanics. You put things in the box and you say, well, I'll take a limit eventually. So that's field theoretical way of thinking of Bernoulli map. It's a field. And now this field has to satisfy a condition. It's not a map because we are not moving any place. It's just lattice in a state line. There's a condition which is local, which basically says, I look at my neighbors and I have to do what I'm told to do. But for the whole block, it has to be enforced by a global equation. And in this case, it's very simple to think about. You can think of phi's as a vector of n fields, m's as a vector of m sources. And then there is a matrix that says, I look at the field and I compare it with a neighbor, and that's obtained by shift matrix. Shift matrix, when applied, looks at the neighbor above the diagonal. And this equation is now written as a matrix equation. And for every m, this is a matrix, you can invert it. So for every m, you can analytically compute phi. And if this s is an integer, then it turns out it's some bunch of rational numbers. So you can compute infinitely many of these things very quickly in Bernoulli. It's easy. So you think globally, you have to solve all the problems on the whole lattice. You need global solutions, but the conditions act locally, what we used to call Newton equations, but now we call them partial difference equations for discretization of partial differential equations. The way you solve these systems, there's a matrix, and there will be a function whose zeros you look at. And right now it's a linear function, but in general it'll be non-linear function, and I'm looking for the zeros of this function. Finding periodic orbits in a temporal formulation of chaos is now finding fixed points, in this particular case in a hypercube, which is n-dimensional hypercube, and n is the length of the period, one of these tiles that have to repeat themselves.